Hello students, Mr. Elliott here. How are you today? If you are watching this video on Friday or Saturday, I hope you're having a good weekend and you continue to have a good weekend. If you're watching this on Sunday, I hope you've had a good weekend and you've now rolled up those sleeves. Time to get back to work. Let's do our math lesson. Let's shrink Elliott. And let's make the work bigger. Before you watch the rest of this video, you may want to go back and print up this worksheet here. It should be found directly beneath the video link, and it's called 3.3 line of best fit, and it's the notes for it. You can do this however you want. What I recommend doing is trying out this worksheet on your own. And then pause the video, try out the worksheet, and then start the worksheet back up with me if you get stuck. Or you could just use me and check your answers. Whatever you feel you need. Anyway, let's take a look at this. This lesson is called Line of Best Fit. This is a topic that you did cover in Algebra 1. And this particular problem is about the wave. If you've ever been to a sporting event, they may have done the wave if the game got boring at some point. Anyway, this person determined that a 3-person wave took 2.1 seconds, a 6-person wave took 2.3 seconds, and so on. And our first thing we need to do is we need to, step 1, we need to plot the points. We got to label these axes here. My horizontal axis, I'll go ahead and let that be number of people. And the y-axis, the time in seconds. And let's see, for number of people, it goes by threes but up to 27. How's my x-axis looking? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it appears that if I go by threes, I will be able to fill up the x-axis. So 18, 21, 24, 27. Now, with this much graph paper, you want to fill up as much of the graph paper as you want. I noticed that the top time on the y-axis is 7.5. If I count this up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have enough room that I can actually have each one of these be a half unit. So this would be 1, 2, 3, 4, 5, 6, 7. And it appears that my last point will go a little bit over, but we can work on that. Here we go. Let's graph these points. I have the point 321. So 3, 2.1. So we'll just make a little estimate. Put it there. 6, 2.3. 9, 3.5. 12, 3.7. 15, 4.4. 18, 4.8. 21, 5.9. 24, it's exactly 6.5. That's nice. And 27 was 7.5. Now, this is usually how a real life graph will look. It's not going to follow a perfect linear line or a quadratic line, but it's going to follow something that's close to a linear model or exponential model or a trigonometric model. Who knows? But in this case, when I look at these dots, they really look like they form a linear line. So what we're going to do next is we're going to draw a line of good fit. We usually don't say good fit, we usually say best fit. And a line of best fit, couple pointers, it doesn't have to touch any of the data points, but it should represent the overall trend of the data. I always tell people, try to make sure that you have the same number of dots above and below the line, and that it also follows the trend. if this were a statistics class, we could numerically figure out how good our line is. But because it's not a statistics class, we're just going to estimate, do the best that we can. I'm going to say this is my line of best fit. Okay. Now, a couple things about this graph. You can't have negative number of people, so I really should not have included this part with my graph. It's kind of embarrassing. I'm just going to kind of scratch it out. And this end is their number of people. We could keep throwing a lot more people into this. So I'm going to put an arrow on at the graph to demonstrate that it goes on forever. All right, step 3. So with our line of best fit, we now want to come up with an equation that we can use. So with that equation, we can then predict how long it'll take larger sizes to do a wave, or we could also figure out if we have a population, how long should it take for them to do a wave. So it says pick 2 grid points that are on your line. You want to find, it'll be easiest for us if we can find a couple points that go through nice, happy intersection points. Like right here, my graph is passing right through 9, 3. And also right here at 18. It looks like it's passing through 18, 5. Find the slope and the y-intercept, then write the equation. So with this equation, my slope, m, y2 minus y1 over x2 minus x1, and I end up getting 2 over 9. The y-intercept, well, we can use our graph for our y-intercept. Looks like my y-intercept, it's a little above 1. I'm gonna say 1.1. But I guess, oh man, I didn't have the math showing. I had to zoom out here. Sorry about that, everybody. I was focused in on the math. I forgot to look at the screen. That's not good math teaching. Sorry, everybody. Elliot will do better. So, I'm actually going to do this backwards. I'm going to put the equation using point slope form. I'm going to do part C first, and then I'm going to use that point slope form to find the y-intercept and answer this question here. So, point slope form, 2 over 9 times x minus one of those coordinates. The x, I'll use this coordinate 9, 3. So, x minus 9 and plus 3. And if we simplify this out, distribute this, I get 2/9 x minus 2/9 times 9. Those 9s beautifully cancel out, and you're just left with a negative 2 plus 3, and you get 2 over 9x plus 1. Oh, exactly, 2 over 9x plus 1. So if I used my graph, I would say approximately 1.1. If I used the algebra, I would get an answer of 1. Both answers are close, and I would actually accept this decimal approximation because there's nothing exact about a line of best fit. It is going to be a little bit more of an approximate, but it's always good to show your work. Okay, so this is going to be my equation. Y equals 2x y equals 2 over 9x plus 1, and let's just answer some questions about what all of this means. Independent, dependent variables. Rule of thumb is the x-coordinate is usually the independent variable, and the dependent variable is usually the y-coordinate. But you can also think about it in terms of what's happening in this situation. Is it that the number of people is affecting the time? Is the time dependent on the number of people, or is the number of people dependent on the time? And that's so confusing to think about when I word it like that. But in this particular case, the time is dependent on the number of people, because the more people we throw into the mix, the more time it takes. Which is what I said earlier about the x and the y coordinate in this particular case. So in this particular case, the independent variable is the number of people. People. While the dependent variable is the time. And because we're talking about time, you got to measure it. Seconds. Slope. The slope is 2/9. And when you think about slope, you think about rise over run. So as we rise 2 seconds, we ran, well, that added 9 more people. So if our x coordinate changes by 9, so if we add 9 people, if we add 9 more people, because 9 stands for people, 2 stands for seconds, if we add 9 more people, comma, the wave will last 2 more seconds, according to the slope, rise of 2, run of 1. And we mentioned the if part because that's the independent variable. If we add 9 more of the independent variable, that's going to change the dependent variable by a factor of 2. The y-intercept of our line. Well, the y-intercept in my particular equation is 0, 1. And 0 is the x-coordinate, so 0 stands for people, 1 stands for second. So this means that 0 people will take 1 second to do the wave. Doesn't make sense, does it? Well, it's not always going to make sense when you're having an equation, a mathematical equation that you're trying to apply to a real-life situation. It's going to fit this real-life situation as best we can. That's why it's called a line of best fit, but it's not always going to be perfect, and this is a good example of that. The real-world meaning doesn't make sense, but you aren't going to be testing how long it takes 0 people to do the wave. We want to know how long it takes 50,000 people to do the wave. At least I do. Reasonable domain and range for this function. Domain. Is it reasonable to have 0 people do the wave? No, that's not reasonable. But, wait, is it reasonable to have 1 person do the wave? No, it doesn't seem reasonable to me to have 1 person do the wave. But can you have 2 people do the wave? Sure. Person 1, person 2, do the wave, 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 wave. I feel it's reasonable to have 2 people in my domain. So 2. What's a good maximum number for the domain? Well, think about stadiums. How many people fit into a stadium? I've been to Michigan football games that had 110,000 people in it. That's the biggest wave I've personally ever witnessed. So I'm going to put 110,000 people for a reasonable domain. Reasonable range. Well, 2 people is going to take the least amount of time. 110,000 people is going to take the most amount of time. I'm just going to take both of these numbers, plug them into my equation, see what decimal pops out, and then I'll be good to go. First need to find my the calculator that I'm always telling you kids to use. So let's go. If I go 2 divided by 9, gives me a decimal of 0.2 repeating. I multiply that by 2 for that x value, and I get 0.4 repeating, and I add 1, and I get 1.4 repeating. How many decimals do you need to put into your work? I notice up here they're only going 1 decimal. Consistency. If they're just using 1 decimal to me seems reasonable. Same thing if I plug in 110,000. I start with 2 divided by 9. I multiply that by 110,000. And I get a big old number. I add 1, and I get one larger than that big number. So 24,445.4 seconds. And why do I feel it's a reasonable domain? I use words in my description, but yeah, I think 2 people is a reasonable number of people to do a domain, and biggest stadium I've ever seen is 110. And that's my explanation is why it's a reasonable domain, and the work that I showed would get you that range. Anyway, that's it, everybody. Tomorrow we are going to have some book problems, and if you want to look on the Excel worksheet, that has the schedule of what problems we're going to be working on out of the book. And I hope you have yourself a wonderful rest of the weekend, and I will see you on Monday. Bye-bye, everybody. Oh, wait. Got to make Elliot bigger. Big Elliot. Have a good weekend, everybody. Bye-bye.